I don't know if the three next speakers are there and if they want to make a quick try to screen sharing, if they want to. I don't know.
Yes, I'm here. Can you hear me?
Okay. Yeah, we can hear you.
Too.
I can try. Can you see my?
It's loading. It's loading.
It's paused.
Yeah, we can see the first slide. I don't know if you want to try to go to the next one to see. Yeah, okay, it's working perfectly. Thanks. I don't know if Olivier and Pauline, if you want to try to share.
Yeah, I can also try.
Okay.
Just a second. It's this one. So
you can see your desktop. Yeah. Okay.
Perfect.
Great.
Okay, and I will.
Yeah.
Yes.
Yeah.
Okay.
Working
perfect.
Nice.
I can try.
Yeah. Yeah. Okay. Pauline, you have to stop sharing.
Yes, I missed my. Okay. I have to do it, or can it do someone?
You have to. I think you have to close it.
No, that was the wrong button.
On top of the screen, I guess you have stop sharing somewhere.
Why?
No. You are stuck.
I have no idea what I'm doing. I can't find my Zoom anymore.
You can't open it anymore. You have to close it.
So.
Yeah, you can't open the Zoom program anymore. You have to close it using the thing at the top of the screen.
What do I have to do?
I don't know if we see normally really on top of the screen you have the possibility, but I don't know if we see what you can see also, or if you have an additional option.
I have it. I have it.
Great.
I'm sorry.
No problem. That's why we are testing that now.
Okay. Right. Can you see my screen?
Yeah, working perfectly.
You can see this works too?
Yeah.
Okay, good.
Thank you. Okay, so good afternoon, everyone. So I have the honor to be the last chairman of this ESICUP meeting. So much pressure. Okay, no pressure for the speakers. Please feel comfortable. So we have three speakers for this last session, and the first one is Jeroen Gardeyn. I don't know if I pronounced it correctly.
Yes.
Okay, great. So the floor is yours.
Yes, I hope everybody can see my screen.
Yeah.
Okay, so today, my name is Jeroen Gardeyn, and I'm a PhD student at KU Leuven under the supervision of Tony Wauters. And today I'll be presenting a goal-driven rune and recreate heuristic for the 2D variable-sized bin packing problem with guillotine constraints. So I'll start off by giving a very brief definition of the problem, followed by explaining how the heuristic works. And I will also look at some computational results, and I'll close the session by giving a visual demo of how the algorithm works. So first, the problem definition. I think many of you are aware of how the bin packing problem works, but in short, you have a set of small rectangles, commonly referred to as items, which have to be positioned inside large rectangles, also known as bins. And these items, they have to be fully inside the bin, they can't overlap, and the goal is to minimize the number of bins you need to pack all the items. So that's a general 2D bin packing problem, and for this heuristic, we also consider the guillotine constraint. So every pattern must be able to be cut by making exclusively use of edge-to-edge cuts. The heuristic also supports some variants of the 2D bin packing problem, such as 90-degree rotation of items and what the literature refers to as variable-sized bins, which are so the general 2D bin packing problem. All the bins are unique, are the same, are identical. And in this variant, you have a set of bins of all kinds of different sizes and shapes. Well, they're all rectangle, but different sizes. So the heuristic, first I'll explain how a solution is represented. So a solution is represented by a set of patterns, and each of these patterns is actually a rooted tree, as you can see in the figure. This data structure is similar to data structure many others use, such as Côté et al. And it contains 3 types of nodes. You have the item nodes, which are the gray ones. I see if I can have a laser. Yeah. So these gray nodes here, they represent items in the tree. You have the green nodes, which are leftover nodes, and these represent free space in the bin. And then you also have structure nodes. These are the white nodes, either denoted by a V or an H, and they define the structure of the pattern in a hierarchical way. And this V or this H denotes how the children should be cut. So for example, here the root is a V. This means that you need to make a vertical cut to create the 2 children of the node. So you cut right here. This data structure allows for simple insertion and removal of items, which is, so it's a very flexible data structure. And it ensures the guillotine constraint. It's impossible to make a pattern using this representation that is not compatible with the guillotine constraint. So this is a general overview of how the heuristic works. As the title suggests, it's a heuristic based on the ruin and recreate paradigm. So in each iteration, we're going to partially destroy the solution and rebuild it afterwards. And of course, we're also going to evaluate it. And I'll be using this figure throughout my explanation to give it some more structure. So I'll first start by explaining how the ruin procedure works. During the ruin procedure, we will remove a number of nodes from the solution. These nodes will be selected at random, and it can be either item nodes or structure nodes. So for example, in the first example here, the node, this item node containing item number 3 is selected for removal, which just results in item 3 being removed. Very simple. In the second example, a structure node on this first level is selected for removal, which results in the entire right side of the cutting pattern being freed up. And on the third example, the root of the tree is selected, which results in the entire cutting pattern being deleted from the solution. So, as I said before, these nodes are selected at random. The number of nodes you remove is a parameter. And the goal is to create large or relatively large regions of contiguous leftover, so free space in the solution, because it's always easier it gives you more flexibility. And another thing is related removal. So for example, in the second, for instance, in the second example here, item 2 and 3 are removed at once, and it is likely that they will fit well together again somewhere else in the solution, because they share the same width. So as the patterns get better and better and better, you start removing areas of your solution which might be which might fit even better somewhere else. So that's a quick explanation of the ruin strategy. And now I'm going to explain the recreate procedure. So after the ruin procedure, we've got a solution with a lot of holes in it, and we also have a set of items that's currently not included in the solution. So during this procedure, we want to add every item back to the solution again. We'll do this one by one, and every time we select the most restricted item at that time. And by restricted, I mean the item that fits in the least amount of possible nodes inside the solution. So once we've chosen which item to insert next, we're going to evaluate all the possible options to insert it. And if there are no options, we will open a new random bin if that's allowed. So all insertion options are evaluated using this cost function. I'll start at the bottom. Each leftover node, so each green node has a certain value associated to it, and this value increases polynomially according to its area. So bigger leftover have way more value than smaller ones. And the cost of an insertion option is actually the loss in leftover value, in the total leftover value of the solution by inserting this part of or item. This is more visual explanation of the recreate procedure. So, for example, we want to check how this item here, this gray item, fits inside this random leftover node, and there are a maximum of 4 possibilities how it could be inserted inside this node, if rotation is allowed, at least. And we can see that option B here has the smallest cost because it preserves this very large area of leftover. We don't waste a lot of leftover. For example, this one is the most expensive one, and we see that the leftover is split almost in 2 halves. So these are the ruin and the recreate procedures. But the title is a goal-driven ruin and recreate heuristic. So I'll be now explaining the goal-driven aspect of the heuristic. So due to the nature of this problem, every feasible solution that has the same total area of bins used is identical. So once we found a solution with a certain bin area, we're not interested. We're only interested in solutions that have less bin area than the current best one. So the idea of this goal-driven procedure is to force a limit of usable bin area for the recreate procedure, and we're going to keep decreasing this limit each time we find a feasible solution. And so the recreate phase must respect this limit. And of course, this will result in temporarily incomplete solutions, because if we decrease this limit, we won't be able to initially fit all the parts inside the solution. But the idea is to gradually guide the solution back to feasibility. And once feasibility is reached, a new goal will be set. So if we look at it graphically, so for example, right here, and this is the time axis, this is the algorithm running. We have a solution, and we see that almost all items are included inside the solution, and suddenly we can fit all of the items, which triggers a decrease of the bin area limit, and from then on we are forced to use less total bin area than before. So this keeps going until a time limit is reached, and of course each new goal, reaching each new goal is harder than the last one. So this is this part of the flowchart. So we ruin the solution, we recreate it, we evaluate it and accept it or not. I will explain this later on. But if a solution is complete, so if it's feasible, if it contains all the items, the bin area limit is lowered, and we keep going. We just keep going. So the last 2 parts of the flowchart, evaluate and accept. So as I said before, the goal is to guide the heuristic towards a complete solution again. We're not using a purely hill climbing approach, only accepting better solutions than the one before, but we're using the late acceptance hill climbing. And this gives us the ability to, unlike other meta-heuristics such as simulated annealing, we don't need to define how much better a solution is than another one. We just need to define if it's better, yes or no, or if it's equal, but we don't need to define how much better it is. So we define a solution S1 to be superior to solution S2 if solution S1 contains less area of excluded items. So the sum of all the items which currently do not fit in the solution. If this is less in S1, S1 is the superior one. And if it's equal, we look at the total value of all the leftovers in the solution. So all the green nodes in the solution, all these values combined, we look which one has the most value, and that one is superior. So this way we give well, solutions that are closer to feasibility are better. So quickly, there's also a multi-threaded variant in which each thread runs its own separate local search, but they share a global bin area limit, and each thread can lower this limit, and this limit is also applied to all the threads. So it's a race between the threads to lower this limit. And this is specifically important for instances with many different bins, because it ensures diversity. Because with many different bins, you can have a combination, two threads which have a vastly different combination of bins that they use, and they are very close in quality, but it's very difficult to go from the one solution to the other one. So we need some kind of a little bit of diversity here. So now I'll go over to the computational results. We tested on the classical 2D bin packing problem with oriented parts, so no rotation, and guillotine cuts on the very well-known instances from Paquay and Wang and Martello and Vigo. And if we compare it to other algorithms in the other guillotine algorithms, we improve upon the state of the art only by a small amount, but we're already very close to the lower bound here. I forgot to mention this is running 8 threads and 10 minutes of runtime maximum. We also tested on the variant with rotation. So while in the previous, in the variant without rotation, we always match or improve upon the previous best algorithm. In the variant with rotation, it's more of a mixed bag, where we can see that the end result is still very competitive. And then we also tested on some of the more popular instances for variable sized bins, and in these instances, it's a very big difference between the previous state of the art. Here it's 3%, here it's less, but these instances are very small. And this is another data set for the variable size bin packing problem. And we see that just always is always better, sometimes more significant than other times, but it's consistently significantly better than the previous best. Okay, then I'll end with the demo. So this is a visual representation of the algorithm. You see the red items on top are the items that currently do not fit inside the solution. On the left-hand side, you can see on the left bottom side, you see the current utilization, so the current best found feasible solution, which keeps increasing and increasing. And on the right side, you see a curve, you see a graph displaying the current percentage of included item area. So it keeps going to 100%, and then a new goal is set, voila, and then it drops back again, and it slowly climbs back to hopefully 100%, and then it keeps going, but eventually it becomes quite hard to reach new solutions. So as you can see in the graph on the right hand side, it takes longer and longer to reach these new better solutions. So yeah, I think that's about it. The demo, well, we find a better solution, but it takes some time. Yeah, okay. Now we found it. So it keeps on running for a couple of more minutes, but it's not possible to, well, we don't find any better solution. So these are some references for the algorithms I compare with. Okay, thank you for your attention. If there are any questions, I'll be happy to answer them. Thank you.
Thank you very much, Jeroen. Nice presentation. Is there any question in the audience? Yes, Florian.
Yes, so thank you for the presentation. The results look very good. My question is, for variable size bin packing, how do you handle a changing bin? So you empty one to decrease the limit, and then if you need to change with another bin type that you're not using.
Mm-hmm. So well, we tried a lot of different strategies, but in the end, the best strategy was just to. So when we ruin the solution, there will be some slack in the limit of bin area. We will have some bin budget to work with, and each time, if we select an item and there's no possible insertion option, we just open a new random bin which fits inside the limit. So we don't do anything. We don't try to do anything smart or come up with some rule of thumb to open bins. We just select a random one that doesn't break the limits, and we open that one and we start filling it up.
Okay, so have you tried on variable size bin packing with more diversity in bin sizes?
Compared to,
maybe it would be harder in this case.
Yeah, well, the demo I showed only contains 2 bins, but these benchmarks, especially these ones here, some of them contain 6 different sizes of bins, and they range from they vary a lot. So
Okay.
I don't think there are, maybe in this benchmark there are instances with more different bins, but yeah, I think 6 is the maximum we tested, but I don't see a reason why it wouldn't work for more different types.
Okay, thanks.
Any other question?
I have a question, so sorry, I can't see where to raise my hand. So if you limit this to a single thread, what happens then? Because I think the results that you presented, they are for 1 minute and just a single thread for variable size bin packing.
Can you repeat?
So you mentioned that it's for 8 threads, right? So it's so I just try to understand if this is advancement of multi-threading or this is advancement of the algorithm.
Yeah, I have this. I have tested this on and I've added this on a hidden slide, but I can show it. This is. Can you see my screen? Oh, can you see my screen?
Yes, we can.
Yes.
This is how it scales to extra threads. So these are, I've tested on a subset of this last benchmark set, only with, I think, if I recall correctly, with the instance with a lot of different bins, because the more different types of bins you have, the more difference there's. Well, the more different solution qualities you can reach, so the more fine-grained comparison you can do, and this is how it scales with multiple threads. So the first couple of threads increase the solution quite significantly. Like you going from 1 to 4 threads, you gain like 0.5% in yield, but after yeah, you quickly get diminishing returns. So it also works reasonably well with one bin. With one thread, I think. Well, with one thread, we would certainly also beat this score, but to get the last mile, to go the last extra mile, adding more threads helps. I hope that answers your question.
Yes, thank you very much. Just a second question very quickly. So in terms of runtime, so how the runtime impacts? I mean, the range between 1 minute to 10 minutes and maybe longer.
Yes, that's the other that's the other chart I've hidden. Yeah, it's kind of the same graph. It's in the beginning. This is 1 minute. This is 30 seconds. I think this is 1 minute, 2 minutes, 5 minutes, 10 minutes. It also increases. The quality increases, but it also flattens off. Yeah. But I think the quality of this heuristic is not in its speed, because if you really limit the time, some of the other algorithms, especially in the instance with identical bins, will perform slightly better, I think. But yeah, if you allow it to run a bit more time, we can still improve quite a bit on the solution.
Yeah, thank you.
Thank you very much.
Thanks.
I propose that we move to the second speaker so that we are still on schedule. Thank you very much, Jeroen, for your presentation.
Thank you.
So, Olivier Lalonde is our next speaker.
Okay.
Yeah, it's working. We can see the screen.
So I can
It's not
start?
in full screen. I don't know if it's on
Oh,
8%.
that's right.
I don't know.
Yeah. Right. Can you still see my slides?
Yes.
Okay, right. So can I start?
Sure, the floor is yours.
Okay. So hi, I'm Olivier Lalonde. I'm an undergraduate from the University of Montreal in Canada. And in this talk, I'll be presenting an algorithm that I, together with Jean-Fran Côté and Bernard Gendron, have developed for the multiple knapsack problem. So in this talk, first I'll define what the multiple knapsack problem is. I'll then present the standard approach for solving this problem and compare it with ours. I'll then describe a column generation procedure for generating upper bounds in our algorithm. I'll then show how this column generation procedure is integrated in the breadth and press algorithm. Finally, I'll describe a dense neutral heuristic for solving the packing subproblems that are encountered during the course of our algorithm, and I'll end by presenting computational results. So the multiple knapsack problem is, in a sense, an extension of the usual binary knapsack problem, where there are multiple knapsacks to which items may be assigned instead of only one. So we're given a set of n items, each with a non-negative weight wj, as well as a non-negative profit pj, as well as a set of m knapsacks, each with a non-negative capacity ci. And the task that we wish to solve is to find a subset of items of maximal total profit that can be feasibly assigned to the m knapsacks. So the multiple knapsack problem can be formulated using binary integer programming using mn binary decision variables xij, where xij controls whether the jth item is assigned to the ith knapsack or not, equaling 1 if this is the case and 0 otherwise. In this model, the objective is the sum of the profits of the items that have been assigned to a knapsack, where this inner sum equals 1 if the jth item has been assigned to a knapsack and 0 otherwise. The first set of constraints here that we refer to as capacity constraints say that for every knapsack, the sum of the items, the sum of the weights of the items that have been assigned to said knapsack does not exceed its capacity. And the second set of constraints here say that for every item may not be assigned to more than one knapsack. So the classical approach for solving the multiple knapsack problem consists of branching directly on the xij in the model that I just showed you. And this is used in many previous state-of-the-art algorithms, some of which are listed here. While this approach works well for small instances and also works very well as a heuristic algorithm for coming up with solutions that are very close to optimal, for certain large problems, the search space being of cardinality of order 2 to the nm becomes unmanageably large for such algorithms, and you can never actually get to the optimum. To get around this problem, we replace in our approach, we replace the mn decision variables xij by only n decision variables tj, where tj it controls whether the jth item is assigned to some knapsack at all, being equal to 1 if this is the case and 0 otherwise. Our strategy is then a two-steps approach. First, we perform branch and bound on the TJs to identify promising subset of items, and once such a subset is found, we then solve a packing subproblem to see if this subset can be packed into the M knapsacks or not. One should mention that our approach takes some ideas from a recent groundbreaking paper by Del Amico et al., so, one of the authors of which is currently in the audience. But while our approach is similar to theirs in a lot of ways, there are also some major differences, and we'll see in the results section that our approach works much better in practice than theirs. So for this approach to work, for the first step here, we need a good relaxation to be able to prune large parts of the search space. To do this, we start from the following new formulation for the MKP, which we will refer to as MKP2. This is equivalent to the previous formulation that I showed you, because the capacity constraints are the same, and the second set of constraints, which we still refer to as item constraints, ensure that the desired relationship between the TJ and the XIJ holds, namely that TJ equals 1 if and only if there exists an knapsack for which the jth item is assigned. Furthermore, this last constraint here, which we will refer to as an aggregated constraint, is redundant at present because it can be deduced by summing all these inequalities and then applying this equality to replace the xij's by the tj's, and one gets exactly this equality. The point of doing this is that we can now apply the column generation to this model. And so to do this, we begin by applying Danzisch-Wolf decomposition to this model, where the capacity constraints as well as the aggregated constraint are taken to be subprograms, while the item constraints here are kept in the master program. So for every capacity constraint, for I up to M, we have a class of patterns that looks like this, where the patterns correspond to the items that can feasibly pack into the ith knapsack. And for the aggregated constraint, we get an additional set of patterns here, which corresponds to the possible values of TJs that do not violate the aggregated constraint. Then, for every pattern A, we associate a binary variable which determines whether the pattern is active or not. We make this the following standard identification. And inserting this identification in the previous model, we get this reformulation of our reformulation, where these are the item constraints. This is the same objective as before. And this new constraint says that exactly one pattern be active for every class of patterns. Now, from this, we drop the integrality constraints on the YA, requiring only that it be non-negative, thereby obtaining a very large linear programming model, which has an optimal value Z star, which we'll call ZL2, which is an upper bound on the optimal solution value of the original problem. This is then solved using a standard column generation approach, where the pressing problems are equivalent to knapsack problems, which are easily solvable using combo. One should mention in passing that the relaxation that we obtain in this way, which we call L2, dominates all standard relaxation for the MKP, which can be found in the literature. Among them, the linear relaxation of the original formulation, the surrogate relaxation of the original model, which amounts to summing up all capacity constraints, as well as the usual Lagrangian relaxation L1, which amounts to dualizing the item constraints in the original model. And so from this, conjugation procedure is then integrating in the following branch and press scheme. So first of all, we solve the LP model using column generation. If the upper bound obtained here is smaller than the current lower bound, then the node is simply pruned. But if this isn't the case, we move to checking if all TJs are integer. If this is not the case, then we choose a TJ which TJ star fractional to branch on, and we quit the node. Otherwise, we check if all the Xij stars are integer. If this is the case, then we found this provides an optimal solution to the current node, and we'll leave the node. If not, we solve this packing subproblem corresponding to the TJs, meaning we take the subset of items with corresponding TJ star equal to 1, and we check if these items can feasibly be packed into the M knapsacks or not. If this is the case, then the optimal solution of current node has been found, as the optimal value of the corresponding solution will be equal to the bound found here. And once again, then we've solved the current subproblem. Otherwise, what we do is we add a no-good cut to our original model to exclude the solution that we've just found, which is unfeasible, and then go back and cycle until one of these two stages is reached, and we leave the node. So the packing subproblems that are encountered during the course of algorithms, our algorithm are of the following form. We're given M bins, each with a given non-negative capacity Ci, as well as n bar items with weights Wj greater or equal to 0. As mentioned, these items in the context of our algorithm are those such that the corresponding Tj star is equal to 1. And the decision problem that has to be solved here is whether the n items that were given can be feasibly assigned to the M bins or not. The corresponding, this problem can be formulated as an integer programming problem using, once again, mn, the binary decision variable xij, where again, xij is equal to 1 if the jth item has been assigned to the ith bin and 0 otherwise. Then this constraint simply says that the sum of the weights of the items that have been assigned to the ith knapsack is no greater than its capacity. And this second constraint says that every item must have been assigned to exactly 1 bin. And so to tackle these packing subproblems, we use three solution methods that are run sequentially until one manages to solve the problem. The first solution method is a simulated annealing-based heuristic that is relatively standard for packing problems. The third method is an arc flow. It's based on an arc flow formulation of the same type that has been introduced for the classical bin packing problem by Carvalho in 1999, where bin fillings are modeled using a directed graph, and the resulting model is then solved using a MIB solver such as Cplex in our case. However, the second method that we use, which is a Danzig-Wolf-based heuristic, is, however, completely new, and this is what I will be describing. So to derive it, we begin by applying Danzig-Wolf decomposition to the IP model from IP formulation here. So for every capacity constraint, once again, is treated as a subprogram, and the item constraints are kept as binding constraints. So for every capacity constraint, we have the following set of patterns, which corresponds to the subset of items that may be assigned to the ith knapsack. And once again, to every pattern A, we associate a binary variable YA, which denotes whether the pattern A is active or not. Then we obtain the following reformulation of our original model, where these are the original item constraints. And this is, again, the constraint which says that for every class of pattern, exactly one pattern be active. Now, as opposed to what we did for our reformulation of the multiple knapsack problem, we do not drop the integrality constraint on the YA, but rather what we do here is to restrict our attention to a small subset of the PI that is actually manageable in practice. What we then do is we actually generate all such patterns in the chosen subset and have Cplex solve the resulting restricted model where we restrict the columns to be part of that subset. In our implementation, the subset is chosen to be for a given small value of alpha. We restrict our attentions to the patterns which contain at most alpha items for every PI. And once again, as mentioned, we use Cplex to solve the resulting satisfiability problem, where the PI are replaced by the PI alpha. While this method cannot prove unfeasibility of the problem, it can find an optimal. It can find an assignment of the items into the knapsacks that were solving the problem if one exists, and we shall see in the results section that often does so. In our implementation, we run this for alpha equal 3. If no solution has been found, we move to 4, and if no solution still hasn't been found, we move to 5. And if this for alpha equals 5, no assignment have been found, we move on to the next method. So now for the numerical experiments part. There are experiments that have been conducted on the instances that were generated by Delamico et al. In 2019. These instances are grouped in 5 instance sets, with small and FK1 being relatively easy to solve, FK2 being of medium difficulty, and FK3 and FK4 being relatively hard. All algorithms discussed in the following were coded in C++, and Cplex was used to solve the linear programming models for the column generation part, as well as for the subproblems encountered during while solving the packing subproblems. Also, all running times are in CPU seconds and have been adjusted so that with respect to the processing power of the machine. So first, we'll compare our new relaxation L2 with other existing relaxation in the literature for small and FK1. And here, value represents the average upper bound found by the relaxation. Time is the average time taken to compute the relaxation in seconds. And hashtag instances closed denotes the number of instances such that the floor of the upper bound is equal to the optimal value. And here we see that in both cases, the Lagrange relaxation L2, while being relatively fast to compute, also provides the strongest bounds here by far, and being also extremely only off by 4 on average, and also closes very many instances, in fact, more than half in both cases. For the comparison of overall methods, we'll be comparing ourselves with the high MKP, which was the previous state of the art, which was introduced by Delamico et al., with our algorithm, which we will call BP-MKP. For all instances sets, the number next to the name represents the number of instances in the set. The hashtag opt means the number of problems that have been solved to prove an optimality by the method, and time represents average time taken by the method. We see that in all cases, our algorithm is more efficient than theirs. Moreover, while the difference for a small FK1 and FK2 is relatively marginal, we see that our method is vastly superior for FK3 and FK4, which are the harder instances sets. Being almost 3 times faster and solving also many more instances. And finally, we'll be analyzing the performance of our Dantzig-Wolf-based heuristic that we have introduced a few slides ago. So to test this, during the course of our algorithms, we've recorded the time taken by every method, as well as which method solved the problem. And we also store the problems in memory, and later ran the R-through reformulation on the subproblems to show how the contribution of our heuristic. So in this table, the number next to the instances refers to the number of subproblems that were encountered during the resolution of the problems in the instance set. For here, these numbers indicate the number of problems that were solved by the method, and the time represents the time taken by each algorithm / component when solving these instances. And when we see that with respect to arcflow only, our solver is much more efficient, being almost 4 times faster, and so succeeding to solve a great deal of instances. So to summarize, in this talk, we've discussed a novel relaxation L2 for the MKP. We've then shown how to integrate it in the branch and price algorithm that achieved state-of-the-art results on benchmark instances. And we finally presented a powerful heuristic for solving the packing subproblems that are encountered during the course of our algorithm that significantly reduces the computing time, which in principle ends my talk. Are there any questions?
Thank you very much for your presentation. Really interesting and really clear. Is there any question? Manuel.
Hello, Olivier, thanks for the presentation. I was wondering if you plan to adapt your algorithm to other problem variants, if you think this is a good research direction.
Such as which variants? Because the methods that we use are very specific to this problem, I believe.
Okay, so
no, but I'm not sure how which variant we could adapt this algorithm to, because this is based on this reformulation, which seems to be very specific to this problem.
Yes, if it could be, let's say, generalized to other knapsacks.
The idea of adding additional variables and additional constraints to improve the relaxation, it could be tried for the other problems. And in fact, I have tried this for other problems already, unsuccessfully so far. But yeah, this idea could be used for other problems certainly. Yeah.
Okay, thanks.
Thank you. I have a small question. Is it a published work? Did you submit it?
No. It's we're about to publish it. Well, we're about to submit it. It hasn't been submitted yet, but it's going to be done in the following weeks.
Yeah, I guess so, because you have nice results. So that's great.
Yeah,
okay,
yeah.
Congratulations.
Thanks.
Thank you. I propose that we go to the last speaker, last but not the least, so that we do not finish too late.
Okay.
Thank you.
Yes, so I will take over. Hopefully this time it works.
It worked last time.
It worked, right.
The problem is the end.
Yeah, right. So you can see my screen for the rest of the day. So, okay, and okay.
Yeah, it's working. Perfect.
Okay, perfect. Yeah, so then also hello from my side, and unfortunately, hello for the last talk for this whole conference. My name is Pauline, and I'm working for 4Flow, which is a consulting company, or not now, it's a logistic company, which is offering consulting software and services. And today I would like to share with you how we tackled the 3D bin packing problem with weight distribution constraints inside our software that we sell to our customers. And so to start, right, first a really short introduction about us. So as I already said, we're settled in logistics. We have around about 650 team members operating globally. And our customers are around 300. And last year we just turned 20, which unfortunately we couldn't celebrate yet because of COVID, but hopefully it's coming soon. Yeah, just some of our customers. So it's mainly automotive, but also other industries. This is the team who's working on this project. I was working on it. I'm on the left in in the scope of my master thesis that I did for ForFlow, and included some of the weight restrictions I'm talking about today. And Mario and Henriette are part of the optimization team of ForFlow. And yeah, we're also working on this in the past and will continue in the future. So why do we have to tackle weight restrictions? Another funny picture. I think we already saw some during the last days. Of course, it's important to include weight restrictions and to respect axle load to ensure safety on the road, and also then respect the legal restrictions. And for us, of course, as a company, the more of the real world constraints we can consider, the more feasible the resulting load plan is for our customers. And yeah, so let's have a look at the packing problem that we are dealing with. So we have identical large objects, which are the tracks, basically. Then we have demands that needs to be packed. So here, maybe I can change to the pointer, right? So we have some demands, some box types, weights and numbers. They can be homogeneous, but also strongly heterogeneous, depending on the customer. And as a third input parameter, there has been a routing problem solved before. So all the demands have to be collected in a specific sequence, which leads us to this group number that you can find here on the demands as well. And the task is here to create a packing plan for our truck according to demands. And yeah, target is to minimize the required loading meters, where loading meters are basically the length of the cargo space that is occupied by the packages that are part of this load plan. And with respect to Wäsche, this is a bin packing problem. For this problem, we tackle several constraints. I ordered them with respect to Bordfeld and Wäsche. So on the one hand, we have the item-related constraints. So of course you can, you have different orientations, horizontal and vertical. We consider stackability constraints. So we have on the one hand the self-stackability of each box, but also then the restriction, binary restriction, if a box is over or under stackable with other box types, and an overall load bearing capacity. Then we have positioning constraints, which in our case are mainly related to these group numbers. So this routing order you just saw before. And there you could also, so they give the packing sequence basically, and then you can also allow or forbid to stack different groups upon each other. And yes, on the other hand, there are cargo related constraints. So for us, these demands are all part of transport orders. And if you can have multiple transport orders on one truck, but the target is if not everything is fitting into one truck, so you have to send both 2 trucks, then you shouldn't split the orders. So one order has to go in one truck. Right, and the last thing here is the load-related constraints. There we have the so-called constraint of long arms. So as you see in the picture here on the side, usually the thread box would be close to the wall. But as it's hardly reachable then, because you're coming from the back to unload it, it's moved during the packing here to the front to ensure the reachability. And then also stability. So for this problem, we have a supporting area of 100%. And then we have maximum and minimum weight factors, maximum weight and height factors. That are always just considering the box that is directly on top of one box. So for example, if you have a box that have 10K, it's not allowed to put on top a box that have 4 times the weight of the box below. And yes, then we have the container related constraints, which is our focus on today. We respect the total weight, so the maximum payload of the truck, And what I mainly dealt with within my master's thesis was the weight distribution and then the axle load as the criteria. So to consider all of these constraints, we also decided to use a heuristic. And for us, it's the wall building approach. It's based on the GRASP approach that was published by Mura and Oliveira in 2005 and was adapted actually also in another master thesis for ForFlow by Brandes in 2018. So here you can see the solution building for one solution, wall building solution, and in the end there would be a neighborhood search to find the best solution. So, and now the question is how we include weight distribution. Task is quite clear, I think. We need to consider weight. The problem in practice is that we usually don't have quite detailed data. So I think every customer comes and say, yeah, okay, we have heavy items and you have to consider this while packing, but none of them can tell you where the positions of the axles, what truck types will come to pick up the goods. So this accuracy of available data, this is really a huge issue for us. That's why we decided to go for two different solution approaches. On the one hand, we've developed the so-called LDP method, which is related to the load distribution plan that you also already saw this week. There, the focus is on evaluating the center of gravity of the total mass of the load. And so if a customer can provide this load plan or the detailed information for us to calculate the load plan by ourselves, then we can consider this. But on the other hand, we also have the so-called segment method, which then would work without any additional information. So we just have the dimensions of the truck, the maximum weight, and then we define some segments to distribute the weight like this. Then some words for the approach itself. So the LDP method. So as I already said, there are a lot of different information going in. So it's considering the maximum load that is allowed per axle, also the minimum load. The weight of the empty truck is considered, the maximum payload of the truck. And the result of all of this is this curve, which basically says you, okay, if I have a specific weight loaded, then the center of gravity should be within this interval, and then we can ensure that the maximum axle load is not exceeded. We included this into our wall building packing algorithm. So the idea was to check this after each and every group. So the groups are related to the stops that we have on our tour. And each time one group is packed, then you check the plan. And if the center of gravity is not in this valid interval, then we have some approaches to adjust the load plan. First, we would try to repack only the current group. That's important because we have a valid load plan, then we add some boxes of the next group. And if these boxes then can be adjusted, but if we would adjust the boxes before, then this part would not be valid again. So we try to repack to prefer heavier or lighter boxes to move the center of gravity to the front or to the end. If this is not sufficient, then we would shift walls closer to the back of the truck if this is possible. And even if this is still not sufficient, then we would unload boxes until the load plan is valid again, and then put these boxes into a next truck. And so the advantage of this approach is, as I already mentioned, that we can provide a valid load plan at any point of time, so there will be no axle load exceedance at all. On the other hand, we have the segment method. So here it's really more about the distribution of weight. We divide into several segments. Each of this segment gets an upper bound. This can be entered manually by the customer. And if you have a box that is intersecting with several segments, then you would just consider the proportional weight for each of the segments. Here we then would check after each wall that we build if the resulting weight is still respecting this upper bound. And if not, then we would first try to use lighter boxes out of the same group. And if this is not possible to pack with this, or if then still the upper bound is exceeded, then we would block this remaining space in the segment and then start building here in the next segment. So, and is this good or not? Yeah, luckily we could take the data from our customers. So we had around about 80,000 test instances, and we selected 4 representative truck types for which we calculated this load plan. This is just one of the test instances. Of course, we did some data cleansing, because if you have transport orders of one customer for 1 month, then most likely you will have the same transport order maybe 3 times a week. So we wanted to avoid this and reduce the data set. Also, we just had a look on instances where the weight utilization was at least 70%, and the volume utilization was at least 50% or less than 5%, because we also have this problem when you have really items with a high density, but just a few small. So then there the weight distribution is also quite important. So by doing so, we reduced our data set to around about 500 instances. And we said, okay, our main quality criteria for our approaches is the actual axle load, or mainly the violation of this axle load. That's why we implemented the physical calculation based on the law of lever and the law of moments, which we also already saw this week in more detail by Corinna. And yes, so we implemented this, and then for our standard algorithms, so without the repacking approaches, we packed all the plants and checked that we would have axle load exceedance in 25% of the cases. We had a runtime on average of 0.02 seconds per instance, and around about 9 loading meters. And for the LDP method, so we had quite a huge impact on the runtime, so around about 20% increasing. Still okay for us, because we started with a quite quick algorithm. Loading meters increased about 23%, which was much more than we expected, but I will come to that soon. And yeah, as I said, all the axle load exceedance could be deleted, so there were no more at all. Yeah, so why do we have so much more loading meter? We had the following finding, that the problem with this load distribution plan is that it's quite useful in practice, but it's a quite rough estimation. So in around about half of the cases, there was the load distribution plan was respected, so there no repacking happened. But in the other half of the cases where the load distribution plan was violated, in 84% of the cases, or is it, no, that's wrong, whatever. So most of the cases, just the load distribution plan was exceeded, but the actual physical axle load was not exceeded. So only in out of these 48%, only 6% were actual axle load exceedance. So we did a lot of repacking when it was not required at all. Right, but yeah, in the end there we have an approach where we can guarantee an allowed load plan at any point of time. On the other hand, we had the segment method. Here we had no impact on the runtime at all, so it was less than 5%. And then here are just 2 samples of parameter sets that we tested. So we divided in 3 or 4 different segments and did some tests. One quite good result was this, where we just increased loading meter around 12%, but had axle load exceedance, so could also avoid all the axle load exceedance. Then we had another set where there was also almost no impact on the loading meters of the plan, and we still reduced the exceedance about 50%. So there we're also thinking about maybe adding a parameter so the customer can then decide what's its priority, if it's more about the loading meter or if we have to make sure that the axle load is not exceeded at all. Right. So coming to the conclusion, I think problem description and our solution is clear. Maybe just the outlook. So what we want to continue working on is that we would like to soften this LDP constraints, as we just saw that it's quite rough and often violated when axle load is not violated. And also we of course further work on our repacking approaches to make them faster and more efficient. For the segment method, the idea is to also implement a lower bound. And on the other hand, also we are thinking about implementing boundaries that are not just an upper bound for the weight, but a bound or an interval for the area density. So saying for each area unit, the allowed weight could be between 2 and 10 K, for example. So by doing this, so having this area density for the whole segment, we could also ensure that the weight distribution is not just from the front to the back, but also the left-right balance would be considered. Yes, and that's it. So do you have any questions, comments, suggestions, ideas, what we could focus on in the future?
Thank you very much for this really interesting presentation. José Fernando, you have a question.
Yes, now I'm unmuted. Thank you very much, Pauline. It was a very good talk and on a very important subject, in my opinion.
Yes, I agree.
However, I have to step forward in defense of the load diagram plan.
Mm-hmm.
I think that you are looking at the load diagram plan exclusively as a way of guaranteeing axle load constraints. And yes, it is overshooting in that case. But load diagram plans, I don't know if you have used the diagrams that were provided by the German association or whatever, or if you have computed yourself the diagrams. Because these diagrams do not only look at axle load. They also looked at traction issues, meaning that there has to be a minimum weight on each axle, not only a maximum, but also a minimum weight, so that the truck has traction and does not, I don't know the name in English, starts to move the wheels without really going forward. It also has to do with balance in the sense of dynamic behavior of the truck. So even if you respect the axle load, you may have a truck too loaded to the front or to the rear, and when braking or accelerating, it has a bad dynamic behavior. So using or fulfilling or respecting the load diagram plan is more than respecting just axle load. So when you say, okay, we have used the load diagram plans, and then we're going to check the axle load, and 46% of the times or 42% of the times, it was not a problem. Of course, it was not, because it was not just that you were imposing, you were imposing more constraints on the problem. So I think that I'm not saying that, of course, I understand that axle load is a very important concern because it's what police is inspecting your customers. That's where the fines are. They are not inspecting the dynamic behavior of the truck or safety issues, okay? That's what they pay a fine if they are exceeding. So I understand that. But it is not really because it is a rough estimate. It's because it takes into account more things, in my opinion, as far as I have understood the concept, more things than just axle load. Anyway, I've enjoyed very much your work. Thank you very much.
Thank you. Yeah, you're completely right. So actually that's something we should also consider more in the future. So also that the axle, the load distribution plan, for example, considers minimum axle weight or this balancing or don't know how to say.
Because you can also have the load diagram in the orthogonal dimension. So you are looking along the length of the truck, but you also have the concept along the width of the truck.
Yeah, right. That's actually something where we could extend our...
And when the truck turns left or right, it can turn just because the load diagram is not being respected. So that's why I am saying this is not just axle weight, because when you look transversely to the truck,
sure, that's something different, but actually that's something that we didn't consider. So we calculated the load plans by ourselves based on this guideline, but only did the one from the front to the back and not the other one. So this would be, but this would be actually an idea to work on this in the future, maybe.
Again, congratulations. Yeah. Very nice work.
Thanks a lot.
Julia?
Thank you, and thank you for a fantastic talk. And it's really nice to have contributions as well from companies who are working in this space. And this is a broader question really than directly what you were talking about. But I noticed you had something like 8,000, or was it 80,000? I can't remember counting the zeros, but data sets, 80,000 data sets, which is an incredible resource, and all of us academics would love to get our hands on that sort of data. And just thinking a little bit about Patrick's talk earlier, whether you'd looked at this data to see if there was any sort of clustering of types of loads. So assuming that the load might come from a particular type of organization. So it might be all kind of white goods from some kinds of electric utilities, or it might be some more like goods from stationery or something. So they would be very different sizes and mixes, and whether you've observed any kind of typical sort of mixes in that data that we could maybe as a research group sort of extract, because we can't test 80, well we could try and test 80,000, but I'm sure it takes a long time, but to have a sort of 50 data sets that are really representative would be fantastic. Yeah, that's right. So we didn't do this so far, so I just did some basic analysis about, okay, how homogeneous or heterogeneous is the data, how many different groups do you have, for example, but we didn't then really analyze our results based on the specific input cases. So, or Henriette and Mario, correct me if I'm wrong, if there has anything happened like this, at least not in the scope of my thesis. But I think there is a huge field actually where we could improve and get some more knowledge. Great, thank you.
I have a naive question, but because when you introduced the problem at first, you showed this picture with the VRP, so with the truck and the demand and everything. And there you show, and I know that I have some other colleagues here who are interested in that, you show only pickups actions, right? So it's just a collection of parcels here. There is no delivery, only collection.
No, it could be a delivery or a pickup. So at least, so for us, what's important is that you have what we call a milk run. So the amount of packages loads change during the run. But actually, yes, but we just have either pickups or deliveries. I think we don't have this case where you go somewhere, then you pick something up, then you go somewhere else, deliver, take something other.
Between. Okay, so but you have this problem of just collection, just collecting, just making some pickups within the goods. Okay, this is just what I was interested in. Okay, thank you. Is there
It's
any?
mainly, it's mainly
Yeah.
deliveries, actually. I think this is the main use case, to have deliveries, but yeah, it's tomato, I think, for the.
Yeah, for
local.
us, yes.
Yeah.
For sure. Yeah, okay, thank you. Is there any other question? No? Then I thank you, Pauline, and I think all the three speakers. I hope that you enjoyed the session. And I guess that Julia will say a last word. Yeah? Okay.
I will. Thank you. So yes, thank you very much for everyone. We've had a fantastic attendance at the whole conference, you know, at least 40 people, sometimes up to 50 people in some of the sessions, and that's just been incredible. This online conference has been a real experiment, but I think it's gone well. But don't worry, we will be back in person as soon as we possibly can. So next year we plan on our third and hopefully third time lucky attempt to have the conference in Toledo. It would be lovely if as many of you can attend as possible. We haven't fixed the date yet, but typically it's in the spring, sort of sometimes late March, and it has been up to sort of early May, but around that time. So hopefully we can work around various agendas. So finally, just to thank all of the speakers, in particular to thank our tutorial speakers. Not all are here, but I know Patrick and Manuel are here, for doing these keynotes. They were fantastic, really fascinating, and we'll try to include more of this kind of activity. So I'll leave you to the rest of your Fridays and have a good weekend, and hope to see you next year in person. Thank you all.
Thank you, Julia. Thank you very much for the organization of everything. It was perfect.
Thanks a lot. Bye-bye.
Bye-bye. Bye-bye, everyone.
Thank you. Bye-bye.
Bye-bye.
Bye.